In this podcast, we'll find the zeros of a polynomial function. We can use our different theorems to help us narrow down the possibilities that we have to check. One theorem we can use is this rational roots or rational zero theorem that says, well, our possible rational zeros, they're always in the form of a factor of the constant term divided by a factor of the leading term. So our possible roots or zeros to check are always in the form of a factor of that last term, a factor of 12, over a factor of that leading coefficient, which is 1. And again, it could be plus or minus. It could be positive or negative for these. So we have positive or negative factors of 12. Well, 1, 2, 3, 4, 6, and 12 all divide into 12. And our factor of 1, not so many choices, just 1. So we can take any number on the top with any number on the bottom. This leaves us with the possibilities we could have positive or negative 1, positive negative 2, so on and so forth. This tells us, well, what are the nice rational numbers that we should check? From this, we know 5 could not be a 0 since it's not one of these possibilities we listed out. If we want to find the number of real positive and real negative zeros, we can use Descartes' rule of signs. Descartes' rule of signs says we're looking at the sign changes when we're looking at the positive zeros, positive real zeros. We want to look at the sign changes of f of x. Well, there's one between x to the fifth and negative x to the fourth. There's another one from negative x cubed to x squared, from x squared to negative 12x, and from negative 12x to positive 12. So this gives us the maximum number of real positive zeros, but we could also have complex roots. So we want to subtract off even numbers from this. So we could either have 4, that's the maximum, or we could have 2 positive and 2 complex, or we could have 0 positive and 4 complex. So it's either 4 or 2 or 0 for these positive roots. If we're looking for the negative roots or negative zeros, well, that's the sign changes of f of minus x. So when we replace negative x in for x into this polynomial, we should get negative x to the fifth minus x to the fourth plus x cubed plus x squared plus 12x plus 12. Well, this only has one sign change, going from the negative x to the fourth to the positive x cubed. So these negative zeros, well, we have exactly 1. 1 is the maximum number, but we couldn't have 2 complex roots less than this. So now using all this, we want to find these zeros. When I see there's exactly one negative 0, well, let's test the negatives first. And then once we find that one negative 0, we know there can't be any more negatives, so we have to switch to the positives. So switching this and using synthetic division to help us test. Synthetic division, we're just writing down the coefficients. 1, negative 1, negative 1, 1, negative 12, and 12. And let's check some negative roots, negative zeros. So maybe I'll try negative 1 for my first test point. So using synthetic division, the quicker you can do synthetic division helps for this section. 1 times negative 1 is negative 1. Add it down, I get negative 2. Negative 2 times negative 1 is positive 2. Add it down. Positive 1 times negative 1 is negative 1. Add it down. Negative 1 times 0 is 0, so I get negative 12. And negative 12 times negative 1 is positive 12, so I get a 24. Well, from the remainder theorem, since this last digit was not 0, this tells us negative 1 is not a 0. We need to try something else. Let's try negative 2. So testing with synthetic division again, with negative 2. Everything else is exactly the same. Bring down the first number. So 1 times negative 2 gives me a negative 2. Add it down, we get negative 3. Negative 3 times negative 2 gives me positive 6. Add it down, we should get positive 5. Negative 2 times positive 5 gives me negative 10. Add it down. Negative 9 times negative 2 gives me positive 18. Add it down. Negative 2 times negative 6 gives me negative 12. And here's my 0. This is saying negative 2 is a 0. Since we know there's only one negative 0, we know negative 2 can't be any more of a 0. So that's it. We found all the negative zeros. Let's test with positive numbers. Well, when we test it, we want to use this reduced polynomial, basically where we found the roots. Negative 2 is a root of the original, or 0 of the original, is saying, well, the remaining zeros have to be in this 1x to the fourth minus 3x cubed plus 5x squared minus 9x plus 6 remaining piece. So we're testing this for the remaining roots, remaining zeros. So copying it down again. Maybe try a nice easy number first, like testing a root at 1. So 1 times 1 is 1, bring it down. You get negative 2. 1 times negative 2 is negative 2, bring it down. 1 times 3 is positive 3, bring it down. And 1 times negative 6 is negative 6, bring it down. So it tells us 1 is a 0 here. To check for multiplicity, I would want to also check this one more time and see if 1 is an additional 0. Well, again, this is why it's important to always check this reduced polynomial. So 1 times, bring down the 1, 1 times 1 is 1. Add it up, negative 1. Negative 1 times 1 is negative 1. So positive 2. 2 times 1 plus negative 6 is negative 4. So this is telling me, well, yes, 1 is a 0, but it must have multiplicity 1. 1 only works as a 0 once. So I'm going back to my last step, my last reduced polynomial. And so I want to test for the remaining roots, remaining zeros. In this 1x cubed minus 2x squared plus 3x minus 6. So again, I can use synthetic division to keep testing. I found 1 was a root of multiplicity 1, a 0 of multiplicity 1, so checking for our remaining ones. Maybe I'll check 2 next using the synthetic division. 1 times 2 is 2, add it down, I get 0. 2 times 0 is 0, add it down, I get 3. 2 times 3 is 6, add it down. And yeah, I can see 2 is a 0 of this polynomial. I could check to see if 2 is a 0 of multiplicity 2. It ends up working out. It is not. Or we could look and see what this reduced polynomial is. Well, what's left over is x squared plus 3. So the only way that could be 0 is if x squared is equal to negative 3, or x is equal to plus or minus I times the square root of 3. Once you get down to a quadratic, something like x squared plus 0x plus 3, use other methods, factoring, quadratic formula, completing the square, whatever you need to find the remaining zeros. So to summarize, we found the first 0 is at 1. So 1 is a 0 of multiplicity 1. We found that 2 is a 0 of multiplicity 1. Our negative root we found at negative 2 is a 0 of multiplicity 1. And then our last two zeros, we have the positive I times the square root of 3 is a 0 of multiplicity 1, and negative I times the square root of 3 is a 0 of multiplicity 1. This is saying our original expression, we could rewrite it in a completely factored form of x minus 1 times x minus 2 times x plus 2 times our x squared plus 3 term, or x minus I squared root of 3 times x plus I times the square root of 3. We found all the zeros and their multiplicities for this original polynomial.